Good morning to all. Welcome to our faculty development program on smart cities and Internet of Things, sponsored by AICTE ATAL. Today we have a talk by Dr. Rao Kajita uh, based on recommendation system for IoT applications. Rao Kajita is an assistant professor at NIT Warangal. He has obtained PhD from the University of Hyderabad. His research interests are data mining, machine learning, and deep learning, with a specific focus on machine learning techniques for recommendation systems using various IoT applications he is developing now. His research works have been published in various reputed journals, conferences, proceedings such as pattern recognition letters, information sciences, expert system with application, Journal of Approximate Reasoning, AAI, PRECAI, etc. He has also delivered various guest lectures in several international and national workshops, IITs, NITs, and universities. Now, I would like to invite Dr. Rao Kajita to deliver your lecture, sir. Please come forward, sir.
Thank you very much, Joydal Saka.
Thank you, sir.
Yeah, so shall I share my screen and talk?
Yes, sir, you can share, sir. Yes, it is visible, sir.
All right. Am I clearly audible?
Yes, sir. You are audible, sir. You can proceed now.
Yeah. Thank you very much.
Thank you, sir.
Yeah. Very good morning, one and all. I welcome you all to this session on recommender systems and collaborative filtering for IoT. So, as you all know that the modern life is web supportive, isn't it? Do you agree with me that the modern life is web supportive? We rely on the internet for so many things in our day-to-day life, isn't it? So we read news articles online, we order food online, we procure utilities online, we reserve cab online, we plan for the tour online, as well as we engage in various activities with the help of online. And this has made the internet become part of our lives. So therefore, it is natural that the competition among the vendors offering various services and our interaction with these systems leading to the explosive growth of the data. So currently, we are living in a data era where the huge amount of data is acquired and stored daily. So having too many choices, overwhelming the customer and leading to the state of confusion that what to opt or buy for. So to get out of this situation of the confusion, recommender system technology have been evolved and it reduces the burden on the consumer in making the decisions while doing any e-commerce transactions or while interacting with any of the systems. So today we're going to discuss this recommender system technology in brief, and we're going to discuss the relationship with the recommender system technology with the IoT systems. So the agenda is like this. We're going to introduce what is the recommender systems and where does this recommender system fits in IoT framework and different paradigms of the recommender systems. As it is not possible to discuss all the different paradigms of the recommender system in detail, I've selected one of the very popular paradigm, which is the collaborative filtering. In that, there are various techniques in collaborative filtering again. So I'm going to discuss memory-based collaborative filtering, which gives the basic introduction to the collaborative filtering, and then collaborative filtering via matrix factorization. If time permits, we also look at this geometrical interpretation of the matrix factorization, right? Otherwise, we'll leave it. That's fine, right? So what is the recommender systems? So as I have mentioned previously, that data is everywhere. Lots of data is collected and stored every day. And there is a need to derive some meaningful insights from this data. And this deriving meaningful insights from the data is useful for organizing the data in a better way, and to organize, it helps organizations for better functioning, and it also assists the user in decision making process, right? So to avoid the information overload problem, we need some assistance in the form of the recommendation in our day-to-day life. So that's where actually the recommender system technology has come into the picture, right? So this recommender system technology we might be using in our day-to-day life without even knowing that they are recommender systems. Let's say, for example, when you are using the YouTube, it also recommends some set of videos to you, right? Beside, isn't it? So when you like some video, when you dislike some video, or when you skip watching some video, or when you watching the video till the end, recommender system, I mean, YouTube learns from it. YouTube learns your preferences, what you have liked, what you have not liked. And this learning of the preferences is continuous and it evolves with your experience. And it recommends the systems that makes you feel more enjoyable, right? So YouTube is an example of the recommender system, right, where it uses some recommender system technology to make some recommendation to you, to make you more comfortable with the system. Similarly, when you're watching some videos or some movies in the Amazon or Netflix, it recommends you something like this, right? Customers also watch these movies. It means it is making some set of recommendations to you, right? Based on whatever that you have consumed in the past. Okay. So similarly, when you purchase something in the Amazon or Netflix, Amazon or Flipkart, whatever the e-commerce site, it also says this, right? Frequently bought together. So in addition to this, it is also making some recommendations to you. So these kind of things we often see in our day-to-day life. So it means that we are using the recommender systems. Maybe we are not aware that they are the recommender systems, but we are using these recommender systems in our day-to-day life. And most often we tend to click on what is recommended by the system, because it is not just like that recommending. It is understanding what is our preferences based on our history of the consumption and what we have liked in the past and what we have disliked in the past. It analyzes everything and accordingly it is making that recommendation, right? So why is this recommender system is important? Why not I recommend something very popular? Because the world is moving from one size fits for all to a personalized tailor-made solutions. Because the popular one I may not like because my preferences are different. So if you say that Bahubali movie everyone like, I recommend Bahubali movie. So it may not fit for my preferences. I may be liking something else. I may be liking something something comedy movies or something like that. I don't want to see the action or war movies, right? So each and individual preferences is different. According to this preference, we have to make the recommendation to the user. So for that, the system has to analyze the user preferences from his history of purchases or history of the consumption and make the recommendation accordingly. So suppose if I take the book recommendation, I have a set of books that I've already read, and my preferences on these books also expressed whether I have liked them, whether I have disliked them. So given these preferences to my profile, to the machine learning algorithm, or in specific to the recommender system algorithm, it builds a model based on my history of the consumption and my preferences on these books. Like for example, Red Mass, I've liked Foundation, I like this. There are different references that I have expressed on the different books. And this information is passed to the recommender algorithm or the machine learning algorithm, and it is giving the model, and using this model, given any new book, I can say whether the user would like it or dislike it. And if you would like it, then I can make that, I can recommend that book. If the system says that you would dislike it, I can ignore that book. So like this, you can make it develop a recommender system for umpteen number of domains like book, music, food, whatnot. In every domain, you can apply these recommender systems. So if you, to summarize, recommender system helps match users with the items. So it helps to ease the information overload problem. It is also helping in the sales assistance. So it is two-way fetching. It is both helpful to the user or the consumer, because information overload problem is reduced, because he need not search for everything and look for what he would like it. So instead, there are some set of recommendations based on his preferences, and he can explore the subset of recommendations and he can easily avoid this information overload problem. On the other hand, it is also helpful to the provider, because most often you see that when you're making recommendation, user is tempted to purchase that. So that way sales will be improved. So it is both helpful to the consumer and also to the provider. So this recommender system can be seen as a function that takes the user model and the items as an input and finds the relevance code as the output. So we have given the users and the items. So when you're giving users, you're giving the information about the users. Any query?
Oh, no. নাই তুমি লোৱা তাৰমানে কি আছে এই সপ্তাহ মোৰ এনেও ক্লাছ শেষ হৈছে কোৰ্চ শেষ হৈছে মই তাৰমানে এৰিক্সেমত সিহঁতে এৰি দিব
John, can you mute them?
Yes, I have muted, sir.
All right. So, yeah. So, am I going fast or is this phase okay?
No, sir. It is okay, sir.
Yeah. All right. So, given user model and the items, so information about the users, information about the items. So, when you're giving information about the users information could be the ratings given by the user or preferences given by the user or the demographics of the user, where he is staying, what is his location, or the situational context of the users. Is he with his family, or is he with friends, or is he with the colleagues? So, or is what context he is in at present? Is he in a birthday party, or is he at some other party, right? So that determines the context. Given the information, one or more informations about the user and items information with or without description of the item characteristics, the task of the recommender system is to find the relevance code between these users and the items. To what extent or to what degree the user would like the item or dislike the item. So that's what is determined through this relevance code, and this is used for the ranking the items. And according to this ranking, we'll make the recommendation to the users. We recommend top items to the user. All right. So now you may be wondering that what is the relationship between the IoT and the recommender systems? Why do we need to study these recommender systems in the context of IoT systems? So what is IoT system? IoT system is Internet of Things. It means things that are connected to the internet, right? So not only that they are connected to the internet, they can exchange the information among themselves, or they can send the information to the cloud or the servers, and this information can be used I mean, this information can be analyzed and can be used in various applications, isn't it? If you look at the major components of the IoT system, we have things or the devices. So basically, sensors, actuators, different devices, systems, all this comes here. And we have also gateway, which is for the communication purpose. We have the cloud, which is for the storage purpose. We have analytics, which is for processing the data. And then we have a user interface, which is for the visualization of this analysis performed by the system, right? So these are the major components of the IoT system. And with each of these component, we have some enabling technology. Like for example, if you have a component of things or the devices, we have enabling technology like sensor technology or actuator technology. Like that, we have an enabling technology for this. Similarly, if you take the gateway, we have enabling technology like network protocols and communication protocols. We have different protocols there, right? Similarly, with the cloud, we have a cloud computing technology. With analytics, we have a machine learning or data analysis technology. And with user interface also, we have different technologies available, right? So through this devices or the things or the sensors, you're collecting the information. And this information you're storing, collecting the data and storing this data in the cloud. Excuse me, 1 minute. So through these sensors and different devices, we are collecting the data, and that data is stored in the cloud. Unless you process this data and find the patterns in the data, this data has no meaning, isn't it? So let's say, for example, you want to develop a smart fire detection system where lots of sensors are deployed at multiple places in the forest, right? So unless you process the data collected from the sensors and say that, oh, the temperature is high, right? This data has no meaning, right? Unless you just collecting the temperature information and storing has no meaning. Unless you process this data and analyze this data and detect that there is a fire. Unless you say that, unless the system says this data collected by the system has no meaning. So to enable the importance of the data, to meaning of the data, one has to analyze. There should be some system that analyzes this data, right? So that is what is taken care in the analytics part, isn't it? And that is where exactly our recommender system is also coming into the picture, right? So which processes the data collected by these devices and makes some meaningful it identifies the hidden patterns in the data and it makes the recommendation accordingly to the user, right? So if you look at recommender systems in the IoT device, you have, let's say, that a smart home which has a lot of appliances, smart appliances like smart fridge, smart cupboard, smart washing machine, smart AC, smart lighting system, everything you have. So different sensors you have, different wearable sensors also you have, which collects the data. And once you collect the data, there is a data analytics component which processes the data and it makes the recommendation accordingly to this AICTE, right? So let's consider, I'll give you more examples so that you'll be convincing about why do we need these recommender systems in the context of IoT systems. So consider a household scenario where our Jadal Sarkar wishes to take something new for the dinner, not just aloo. Okay, so consider a household scenario where Jalal wishes to take something new for his dinner. So he asked the suggestion from our system about the possible recipes. So what are the possible recipes based on the items available in his cupboard? So what are the things that the system has to consider? Recipe must be compliant to the Joylal Sarkar's preferences, first of all. So it should be able to mate from what is there in the cupboard and as per the diet provided by the nutrition. So he is not an ordinary person. He always want to be fit, right? So he has a nutrition, he has some suggestions, some diet plan from his nutrition. So it should be as per the diet provided by the nutrition. It's not just like any item which can be made from the cupboard. It should be as per the diet provided by his nutrition. And what he has eaten in the last few days also should be considered, because you shouldn't recommend the same thing again. So if he has eaten something in the morning, you shouldn't recommend the same thing again in the afternoon also, isn't it? So you have to consider what he has eaten in the last few days. And you also have to consider the suggestion from the experts. Experts can be cooking experts, expert can be his friends, right? So you can consider the suggestions from his experts, and you have also to consider how long this recipe will take to prepare and what is the weather condition outside, whether it is cold or that is hot. Based on that also his preferences may change. So considering all this, you can make a recommendation. See this, in this various devices are involving, that are smart devices are involving, right? Smart cupboard, it says that what is available in his cupboard, right? And uh, uh, smart watches or smart health monitoring devices which keeps track of what is suggested by the nutrition as per his height and weight, whatever the calories that has spent on that day, and so on. So if you look at this, there are different IoT devices which are collecting the information, and based on all this information, you're making some recommendation to this Gala, isn't it? So similarly, you can have a device health monitoring system, right, which is installed in the smart devices, like which keeps track of the health of this his smart washing machine or smart fridge or smart lighting system, which keeps track of the device's health, and it can recommend for device service from a particular vendor. So what is the best plan to make a service for this particular device? That can be done. Or you can have a smart fridge, it can recommend purchase of milk from a particular vendor whenever it is getting over. Or you can also have noise monitoring sensor in the house, like so whenever it hears sneezing, right, from you, that whenever it hears him sneezing, It can recommend cold tablets with the best deal, right? So like this, the recommender system can be used at various places within this IoT framework. So I have provided some of the examples, but there are umpteen number of examples that you can think of in this, and it is not much explored also. You can pursue it if you are interested. And the use of this recommender system in smart cities also, it is possible. Like the use of recommender system in smart cities, it plays a leading role to guide citizens in the process of finding services that match with their preferences, and it allows the user to satisfy their needs in an efficient and easy way, right? So that's where this recommender system technology fits in this IoT framework at the data analysis part. So whatever the data is collected from various sensors and from the history of the user purchases, that can be analyzed and make the recommendation to the user, right? So with this brief overview of where this recommender system technology fits in IoT, there are various challenges of the recommender system in IoT. That's a different concept, but let us first understand what is recommender systems and what are the different paradigms in the recommender systems, right? So far we have seen what is the recommender system and where it fits exactly in the IoT framework. All right, so now let's move to the different paradigms of the recommender system. So there is a different kinds of data that is exploitable to the system, right? So based on the kind of data exploitable to the system and what kind of data it is, I mean, is it explicit, implicit feedback or explicit feedback? Based on all these different information about the data, there are different recommender systems. Based on the kind of data that is exploitable to the system, there are different recommender systems. So, and are broadly classified into 4 types. You're gonna see them. If you look at the recommender system as a black box, what it does, it estimates the relevance score and it reduces the information overload. So given the items, set of items and user profile to the recommendation component, it gives us the relevance score. So for example, you can see that item 1's relevance score is 0.9, item 2's relevance score is 1, item 3's relevance score is 0.3, and so forth, right? So the higher is the score, it means that the more relevant it is to the user's preferences. So it estimates the relevance score, and according to this relevance score, it sorts the items and it recommends the top items to the users, top K items or something like that. It recommends to the user. So if you look at the recommender system as a black box, it takes the user profile and the contextual parameters and it gives the relevance score. Broadly, these recommender systems are classified into 2 types: personalized recommender systems and group recommender systems, right? So not from the technical, so in general, they are classified into personalized and group recommender systems. So in the personalized recommender systems, you'll be taking the individual user's profile and the contextual parameters, and you make the recommendation accordingly. Whereas if you go for the group recommender systems, you consider the preferences of the members of the group. Like group could be a family, group could be a set of friends who are going for the tour, group could be a set of friends who are going for the restaurant, group could be a family who is planning to go for a movie, right? So it considers the individual preferences, and by analyzing the individual preferences, it makes the recommendation to the group such that every member in the group is happy about this recommendation, right? So that's what the group recommender system is. But in this, we're gonna discuss, mainly focus on the personalized recommender system, wherein you're making a recommendation to the individual users, not to the group. So it means that individual information only taken into the consideration, and you're making to that individual, making recommendation to that individual. So this is what is a personalized recommender system. And in this, based on the kind of data that is exploitable to the system, we have different paradigms, different techniques, different kinds of techniques in the recommender system. Like for example, collaborative filtering takes the community data information. If the community data is available to the system, you can apply the collaborative filtering technique, and it recommends what is popular among the peers. It means, so there may be users who are similar to me. So what is popular among them? So you look for that popular one in the similar users and you make that as a recommendation to this target user. So that is what the collaborative filtering says. So what is popular among the peers? Peers are the users who are similar to the target user. So you make recommendation accordingly based on the interest of these peers or the similar users. Content based, it exploits this product features information. So item description is also taken into account in the content base. So it exploits this kind of information. So it recommends more of what you have liked in the past. For example, if you have liked comedy movies in the past, it will recommend comedy movies in the future also. If you have liked action movies in the past, it will recommend action movies in the future also. If you have liked war movies, it will recommend war movies. If you have studied fiction novels, it will recommend fiction novels. If you have eaten spicy food in the past, it will recommend spicy food in the future also. If you have eaten aloo in the past, it will recommend aloo in the future, right? Like that, it recommends what is more of what you have liked in the past. So similar, if you are reading more political news, it will recommend political news in the future also. Like that, more of what you have liked in the past. For this, it requires the product features. So it has to say no that what is similar. So to say similar, you should have some base to say that this is similar to this. So for that, item description in terms of the features is taken into account to say that to analyze what is similar, what is not similar, all that, right? So this is one paradigm. So far we have discussed two paradigms. One is collaborative filtering and content based next. The other one is the knowledge based. So which also requires the knowledge models. You see this, you have a look at this, what is the input that we are taking. If you look at these systems, the kind of data that they're exploiting is different. If you take collaborative filtering, it is exploiting the community data. If you take content based, it is exploiting the product features. If you take knowledge based, in addition to the product features, it is also exploiting the knowledge models, right? So what fits based on my needs? So it recommends that. Like for example, if my family is a joint family and there are many people in my family, so my requirement is a 7-seater car or 11-seater car. So a 4-seater car is not sufficient for us. So it understands that. It makes the recommendation accordingly, right? So maybe my family likes black car, right? Or according to my family status, we just need 4-seater car. So whatever it is, or according to lady preference, she need this long strip bag, or according to lady preference, she may need high heels only, right? It understands the needs and the requirements of the user and makes the recommendation accordingly. So for this, knowledge models are required. What are the user needs? What are the user requirements? That is need to be taken into consideration. Like some may need the sport camera, some may need some ordinary camera, some may need very high pixel camera, some may need very cheap camera. So these are all the needs. So based on the needs, you can understand the system can understand the needs and make the recommendation accordingly. All right. And last one, which is hybrid, which is a combination of various inputs and a composition of the different mechanisms. So the ideas of the different strategies, different recommended systems can be combined, or different inputs can be passed as input for the single system, or you can combine the output of the multiple systems. So different ways that you can do this hybridization step, which combines the ideas of the different systems and addresses the limitations of the individual systems. All right. So we have seen the various paradigms of the recommender systems. Different paradigms are the collaborative filtering, content-based, knowledge-based, and hybrid systems. So we're going to see the collaborative filtering technique in detail within the time given to us. All right. So what is collaborative filtering? So how much time do I have? 1 more hour, right?
Yes, sir. Yes, sir.
All right. Excuse me. Yeah. So in collaborative filtering, so what is popular among my peers is recommended, isn't it? So it means that community data is taken into account and it analyzes the community data and identifies the users who are similar to this target user to whom we are making recommendation and what is popular among these peers. So that is also identified and recommendation is made accordingly, right? So the collaborative filtering is the most prominent approach to generate the recommendation system. It's most of the current e-commerce sites use this collaborative filtering technique in one way or the other. There are lots of collaborative filtering techniques, thousands of them are there. So, but generally they are grouped into a collaborative filtering strategy because they take this community data into account in one way or the other, right? So most of the current e-commerce site use this collaborative filtering technique, and it is well understood various algorithms and various variations in each of these algorithms also exist. So the idea is to use the wisdom of the crowd to make the recommendation, right? So there are two basic assumptions here. One assumption is that user give ratings to the items, either implicitly or explicitly. So whenever you consume the item, you rate that item. That's what the assumption is. Two ways, either implicitly or rating or explicitly or rating. So what do we mean by explicit rating and what do we mean by implicit rating? Explicit rating, all of you know it, right? Explicitly we are giving some rating in some numerical number, like we are giving a rating of 5 or rating of 4 whenever you consume something. We usually give, right? Of course most of us don't give the rating, that's a different thing, right? But whenever somebody is giving rating, they give explicitly, right? Rating in the range of 1 to 5. If you like it very much, you give a rating of 5. If you dislike it very much, you give a rating of 1, right? And like that you give a rating. Or you can review it also. You can explicitly say some rating, some review about this item. All these are the explicit information or the preferences that you're passing to the system. What are implicit? Most of the time, we don't usually explicitly give the rating, right? After purchasing the item, we don't even go to that site. Usually, I don't know about you. I'm like that. I usually don't give rating to the items that I've consumed, right? I again don't go to the website and open it again, write a review about it. All that we usually don't do in a busy life, isn't it? So what the system does in that case should have some information about whether we have liked it or not, isn't it? This, like for example, you take YouTube. Every time you don't click on the like button or you don't click on the dislike button, though you like it or though dislike it, you don't express it explicitly. Am I right? Right. So what does the system do in this case? It derives the implicit ratings based on our actions. Like for example, if you skip watching some video at the beginning itself, so the system may implicitly derive that you didn't like that video. Suppose if you have watched a video till the end, the system may implicitly derive a preference that you have liked that video. Like that, based on your actions, your interactions with the system, it implicitly derives some meaning about your interaction, and that implicit meaning is used as an implicit preferences that you have expressed about a particular item. And it can use that implicit rating that you have given about the item to make a recommendation to you. So the assumption is that user gives ratings to the items either implicitly or explicitly. Second thing is that customers who had a similar taste in the past will have a similar taste in the future also. So this is what the second assumption is. Let's say, for example, myself and Joylal Sarkar has a similar taste in the past. So it assumes that in future also we have the similar taste, right? So that's what the second assumption is, right? And in a pure collaborative filtering approaches, the input is only a matrix of the user item ratings. So user item rating matrix is given to us. The output is a numerical prediction indicating to what degree the current user will like or dislike a certain item. It means the rating prediction, or it can be a top and list of the recommended items based on the prediction scores. So there are two possible outputs. Either you're just giving the rating prediction or you're just giving the recommendation as an output by just sorting them according to the relevant score, and you can make the recommendation accordingly. Top K items you can, top N items you can recommend, right? So if you look at the problem, so the problem is like that. We have given the user item rating matrix. So here the items are the movies, but you can generalize it. Item can be anything. Item can be music, item can be movie, item can be book, item can be anything else, right? So the item can be shoes, right? Daily household purchases, whatever it is, right? So item can be anything. So users and the item rating matrix. So if you see that this user item rating matrix, some of the entries are some numerical numbers within the range of 1 to 5, and some of the entries are zeros. So this I can say that the some of the entries are observed and some of the entries are unobserved. All right. So the entries that are observed is that these entries are the entries that the user have already interacted with these items. It means the user have already consumed them, right? So like for example, user 1 has given a rating of 4 to the item 2. Similarly, user 1 has given a rating of 1 to the item 5, right? So it means that he has already consumed them. So all these entries with some numerical number greater than 0 are the observed entries. It means that user has already interaction with these items. And there are some unobserved entries, as you can see that, zeros, right? So these are the entries where the user has no interaction at, right? So our task, I mean the recommender system task or the collaborative filtering algorithm task is to predict these unknown ratings. So there are some known ratings with a value greater than or equal to 1, and there are some unknown ratings with a value is equivalent to 0. So the collaborative filtering task is to predict these unknown ratings, right? So we have given a user item rating matrix, which is of size n by m, where n is the number of users, m is the number of items. An entry indicates the rating given by the user for a particular item, right? And entry equal to 0 indicates the user has not consumed that item. And the goal is to predict these unknown ratings. So like this, you can see, will the user I like an item J or not? Is the question that we are going to ask. If he likes, to what degree he would like this item, whether he would give a rating 5 or whether he would give rating 4 or rating 3, 2 or 1, right? So that's what the task is. We have given this user item rating matrix in which some of the entries are known, some of the entries are unknown. And the task is to predict these unknown entries. So the collaborative filtering techniques are broadly divided into two types: neighborhood-based collaborative filtering and model-based collaborative filtering. So in the neighborhood-based collaborative filtering, collaborative prediction, we select the subset of the users or the items equivalently based on the similarity with the target user or the target item. And we combine the rating to produce the rating for the target user. So we identify the similar users, we take their rating for target item rating, and we combine their rating and give the Alice rating for the user. Alice is the target user, right? So we'll see the example. Don't worry if you don't understand it here. So we'll see it in detail. You will understand. We'll have a better clarity about that. But the point here is that you have some target user to whom you want to make the recommendation, right? So you identify the users who are similar to this target user and you use their rating to make a prediction for the target user, right? So that's what the nearest neighbor based collaborative filtering does. And a model based collaborative filtering, there is one particular model that we're going to discuss, which is the latent factor model. So it constructs a model by identifying the latent factors of the users and the latent factors of the items. And it uses this latent factor information, it combines the latent factors information about the users and the items to make the prediction for the user item interaction. That also we're gonna see, don't worry about that. So let us see each one of them one by one. Neighborhood based collaborative filtering, there are various techniques. There are user based nearest neighbor collaborative filtering, item based nearest neighbor collaborative filtering, like that various technologies in the nearest neighbor collaborative filtering. So we'll see one example from each one of this user based nearest neighbor collaborative filtering and item based nearest neighbor collaborative filtering, right? So before gonna proceed, I've been continuously speaking, but I'm not sure whether you're following it or not. So are you with me so far? Any queries?
Yes, sir.
All right.
Yes.
All right. So in user-based collaborative, nearest neighbor collaborative filtering, the basic idea is that we have given an active user and an item that is not yet seen by the Alice, right? So we have to say whether the Alice would like it or not. So that's the question that we are asking here. So to do that, what we do is that we find the set of users who like the same item as Alice liked in the past and who have rated this item, right? So we are trying to identify the users who are similar to this target user at the same time who have also rated this item I, because our prediction is for item I, right? If the other users also not rated I, there is no point taking them into account, right? So we have to find out the set of users who have liked the same item as Alice liked in the past. It means we are trying to identify the users who are similar to this Alice and also have rated this item I. So we use their rating to predict whether the Alice will like this item I or not. And we do this for all the items that Alice has not seen and recommend the best rated items. So very simple procedure, right? We have a target user. He is the target user, Alice, right? We're trying to identify the users who are similar to them, similar to Alice, and we are considering their ratings to make a prediction for the Alice rating on a certain item. And to what items we make the prediction? We make the prediction for all the items that the Alice has not seen yet, right? So I predict the rating for all the items that the Alice has not seen yet, and I sort them according to their rating prediction, and I recommend the best rated items to the user. So that's what the idea is. Let's see the example that will be even more clear to you. So this is the example, user-based nearest neighbor collaborative filtering. So we have a database of ratings of the current user, Alice, and some other users also given to us. So this is Alice, who is our target user. We have information about the other users also. And there are some items that are consumed by the user and some items that are not consumed by the user. Let's say that there is an item 5 which is not yet seen by the Alice. So our task is to determine whether this user Alice would like this item 5 or not. So that's the question that we are asking. To what degree that he would like it or not. It means what would be the entry here, whether is it a 1 or 2 or 3 or 4 or 5. So that's what we're trying to answer here, right? So what is the procedure? Procedure is to identify the users who are similar to Alice, and I use their rating for item 5 to make the prediction for Alice rating for item 5, right? So that's what the procedure is. So some of the initial questions that we may get is that how do we measure the similarity? How do you say that similar users? So to say that somebody is similar to Alice, I should have something to say that. There should be some measure to evaluate the similarity between the users, isn't it? So how do we measure the similarity? And how many neighbors should we consider? So it's okay, I got somehow similarity between the users I've got, right? So now how many users I have to consider them as a neighbors? Is there another question that we may get? And how do we generate a prediction from the neighbors rating? All right, somehow I've got the similarity measure also. I've also found the number of neighbors. So what next? I have to use their ratings to make the prediction, right? How do I use them? Which formula should I apply to get a rating for the target user on the target item, right? So these are some of the questions that we initially get, isn't it? So we'll solve these doubts one by one. So how do we measure the similarity? First one. So you can measure the user similarity using the Pearson correlation. There are various techniques. You need not restrict yourself to the Pearson correlation, but when it is practically tested on various data sets, for the user-based nearest neighbor collaborative filtering, this Pearson correlation is proven to be the best one. So that's why I'm demonstrating this Pearson correlation. All right. So now a question to you. Suppose before that I have something to say to you, right? So there may be different kinds of users. Do you agree with me? Like there may be a very lenient users who give good rating for all the items. There are very strict users who who don't give good rating even if they like it, isn't it? I may be a lenient user. The least rating that I try to give is 3. Okay. If I dislike it very much, I give a rating of 3. And if I like it very much, I give a rating of 5. Okay, so because I'm a very lenient user, I don't want to give very low ratings to any items, even if I dislike it, right? And Joylal Sarkar, maybe he is a very strict user, right? If he likes it very much, then he give a rating of 3. He likes it very much, then he give a rating of 3. Otherwise, he give 1 or 2, right? So, because there are different kinds of users, can you fix a hard threshold saying that if it is greater than this number, then the user liked it, and if it is less than this number, user disliked it? Can we say that? Can I say that if it is greater than 3, then the user liked it? If the rating less than 3, then the user disliked it. Can I fix that? Any participant? Other participants can unmute themselves and speak up.
Yes, participants, you can unmute and you can ask queries if you have.
You can answer also.
Yeah. You have mentioned my names. I hope all systems should properly recommend to me, sir. Thank you, sir. Please proceed.
Yeah, so I cannot fix a hard threshold and say that if it is greater than 3, user liked it, and less than 3, user disliked it, isn't it? Because each and individual, the way of the giving ratings may be different. Some may be lenient users, some may be very strict users who don't want to give very high ratings. But how can I say that whether user liked it or not? There should be a better way of telling it, right? Rather than fixing some hard threshold, because the rating patterns are different from each and every user. So can I say that if the rating is greater than user's average rating, then the user is somewhat positive about this item. And if the rating is less than the user's average rating, then the user is somewhat negative about this item. This much I can say, isn't it? Right? Because the average rating is differs from individual. I mean, one person to another person, isn't it? So based on his rating patterns only, the average rating would be there. If he is a strict user, the average rating would be 2. If he is a very lenient user, the average rating would be 4. If he is a normal user, the average rating would be 3. So I can definitely say that if the rating is greater than user's average rating, then he is somewhat positive about this item. And if the user rating is less than his average rating, he is somewhat negative about this item. And if I have 2 users, both of them are positive about the item or both of them are negative about the item, then I can say that they are similar users. So overall, if they have some common items and all these common items, if their opinion about these items is same, then they are the similar users. I can definitely say that, right? Let's say a scenario where there is 2 users. When I take their opinion about a particular item, let's say that item 5, so item 3, right? User A, user B, item 3. So user A rating for this item 3 is 4 and user B rating for this item is 3, right? And let's say that user A average rating is 3 and user B average rating is 2, right? So according to this, if you see this, if I subtract this rating from the average rating, so 4 minus 3, it means plus 1. Here also 3 minus 2, which is also plus 1. It means both of them are positive about this item. So it means they have a similar opinion about this item by both the users, though the rating is not same. So one has given 4, another has given 3. But they have the similar opinion because both of them are positive about this item. So let's say that again another scenario where this user A has given rating 2 for item 5 and user B has given a rating 1 for this item B, right? Sorry, user B has given a rating for item rating 1 for item 5. So similarly, if you observe here also, if I subtract the average rating from this individual ratings, 2 minus what is that average rating? 3, right? Here it is 2. 2 minus 3, so it is minus 1. Here also 1 minus 2, which is also -1. So here also they have the same opinion, similar opinion. Both of them are negative about this item. So if you take the common items, if two users express the similar opinion in this common items, you can say that they are similar users. If they express a different opinion on these common items, then they are the dissimilar users. So that's what the Pearson correlation is trying to measure here. So if I say this, here P is the common items by both the user A and B. So A and B are the users. RAP is the rating of user A on item P, and capital P is the set of items rated by both A and B, which are the common items. So I take all the common items. For each of the common item, what I'm measuring, opinion about user A, which is this. I'm trying to subtract this rating from the average rating, and this is also opinion about user opinion of user B on this item, common item P, right? So once I get the opinion by both the users, I multiply them. If both of them are positive, then the resultant is positive. If both of them are negative, in that case also the resultant is positive, right? Because whenever they have the similar opinion, we are getting a positive quantity out of this product. Whenever they have a different opinion, it means one has the positive opinion, the other one has a negative opinion. One of them is positive, the other one is the negative. So in that case, you get negative similarity, right? And this is a denominator which is dividing it by the variance within a single user profile, which is to normalize, to bring them to certain range, in the range of -1 and 1, right? So that's what the Pearson correlation is doing. So coming back to our example, so if you look at the example, we have to measure the similarity between Alice and the other users. So if I apply Pearson correlation on this, I'm getting these similarity values. Similarity between Alice and the user 1 is 0.85. Similarity between Alice and user 2 is 0, and similarity between Alice and user 3 is 0.7, and similarity between Alice and user 4 is -0.79. So as I have mentioned, the possible similarity values can range in between -1 to 1. -1 indicates the most dissimilar, 1 indicates the most similar. So who is the most similar among all these 4 users to Alice? If I look at that, 0.85 is more close to 1, right? So he is the most similar, right? And similarly, most dissimilar, if I talk about, user 4 is the most dissimilar because -0.79 is more close to -1 among all the other similarity values. So the most similar one is user 1 and the most dissimilar one is user 4. So, but if you look at the ratings of the Alice and user 1, they are not same. Observe that. If he is giving rating 5, he is giving 3. If he is giving 3, he is giving 1. Right? So the ratings are not same, but the rating pattern is same. See that? Right? So the rating pattern is same. They have a difference of 2 in expressing, but the rating pattern is same. Whereas if you see the Alice and user 4 rating patterns, give me a second. All right. So if you look at the Alice and user 4 ratings, their rating pattern is also different. If one is giving 5, the other one is giving 1. If one is giving 3, the other one is giving 5. Right? They have a different opinion about this item. If one is positive about the item, the other one is negative about this item. One is negative about this item, the other one is positive about this item. So they have got different rating patterns. So to understand it more better, so let us go for the graphical visualization of Alice rating pattern, user 1 rating pattern, and user 4 rating pattern. So if you look at Alice rating pattern and user 1 rating pattern, they have got the similar rating patterns, as you can see there, right? Whereas if you look at Alice rating pattern and user 4 rating pattern, they've got different rating patterns. So if one is liking, the other one is disliking. If one is disliking, the other one is liking, right? They have got the different rating patterns, right? That's why we have got the similarity value as -0.79, right? So it works well. The Pearson correlation works well in usual domains compared to the other alternative measures like the cosine similarity. So this is how the Pearson correlation expresses the similarity between the users. Now, another question, how do you make the prediction? How many neighbors do you consider, right? So now I got the users, right? Similarity between the users. So number of neighbors, you can consider like top 20 neighbors or top 50 neighbors, but in practice, it is proven that 20 to 50 neighborhood size is good when practically tested. It's like a hyperparameter someone has to test, but when practically tested on multiple real-time data sets, neighborhood size of 20 to 50 is good, right? And if there is another way of selecting the neighbors also, if similarity value greater than certain threshold, then also you can select the neighbors, right? So once you select the neighbors, you can consider the neighbors rating, and you can use that rating to make the prediction for the Alice rating on a particular item, right? So here, how do I combine? I get the opinion of the crowd about this new item to which I want to make the prediction. So I want to make a prediction of user A on item P. So this is what the prediction that I want to make. So I get the opinion from the crowd, right? Which means the neighborhood. If the neighborhood is positive about this item, it means I'll also be positive about this item. If the neighborhood is negative about this item, then I'll also be negative about this item. So what am I getting? I'm adding this opinion that I've got from the neighborhood to my average rating, right? So RA bar is the average rating of the target user. So this I'm combining with the opinion of the crowd or the neighborhood. So how am I getting the opinion of the crowd? I'm taking each and individual from the neighborhood and whether they are positive or negative about this item, and multiplying that with their similarity with this target user. Okay, if they are more similar, you give more weight to that opinion. If they are less similar, you give less weight to that opinion. So this opinion is combined with their similarity values, and we combine these rating differences and add it to this user average rating. So we add or subtract the neighbors bias from the active users average, and we use this as a prediction. So that's how you can make the prediction for the target user. So I'll repeat this process. You getting the opinion from the crowd by getting the opinion from the individual users of the crowd. So this is the opinion, whether they are positive or negative. You are taking their rating and subtracting it from their average rating. So this is either positive or negative. So this opinion you are combining with the similarity values. It means if particular user is more similar to A, then you are giving more weightage to that particular opinion. If your particular user is less similar to the target user, then you are giving less importance to that opinion. So like that, you are combining the neighbors ratings and neighbors rating differences and use the similarity A as the weight, and you use this opinion and subtract or add it to this target user's average. If the overall opinion is positive, then you will get a positive prediction for user A. If the overall opinion is negative, then you will get negative opinion by user A on this item. So that's how you can make the prediction in user-based collaborative filtering. User-based nearest neighbor collaborative filtering. I hope that's clear. Any queries so far? Is that clear? Are you with me?
Yes, yes, sir. You can proceed.
The next one is the item-based collaborative filtering. So if you take the user-based collaborative filtering, nearest neighbor collaborative filtering, we found the users who are similar to the target user, and we combine their ratings to get the rating for the target user on a particular item. So here, in contrast, we find out the similarity between the items to make the prediction. So we consider the target item, which is item 5, and we find out the similarity between item 5 and the other items, right? For example, this item 5 and item 1 and item 4 are the similar items. Let's say that when I found the similarity between the items. right? So now I use this Alice rating on these items to make the prediction for item 5. So what am I doing? I'm trying to find out the items that are similar to this target item, and I use the Alice rating on these items to make the prediction for item 5. So similarity here, it is used as a cosine similarity between the items, but you can go for any other, but see, it is all based on the practical demonstrations, practical experiments, and they have tested with respect to multiple similarity measure. In item-based collaborative filtering, cosine similarity measure is proven to be working well. So that's why they have used this cosine similarity. Similarly, to make the prediction, you can use all the neighborhood ratings, I mean their ratings and the similarity values, weighted fraction of this rating information to get the prediction for the target item. Like for example, 5 is multiplied with the corresponding similarity value plus 4 is multiplied with the corresponding similarity value divided by the overall similarity values, right? And neighborhood size of 20 to 50 neighbors seems to be reasonable for most of the real world scenarios. So what are the problems? So far we have seen in collaborative filtering, we have seen the memory based collaborative filtering, in which we have considered two models: user based nearest neighbor collaborative filtering, item based nearest neighbor collaborative filtering, right? So in general, this collaborative filtering has got some problems. One of the problem is that cold start problem. What is cold start problem? How to recommend new items, how to recommend new items and what to recommend to new users, right? How to recommend new items, because new items means no one might have rated them yet, right? So if no one has rated them yet, how do you consider the neighbors rating and arrive at the prediction? What to recommend to the new users, because new users has not watched anything, their profile is empty, right? So what do you recommend to them, because we don't have any information about them, right? So what to recommend to the new users is also the query. So these are all the cold start problems: how to recommend to the new items and what to recommend to the new users. Some of the straightforward approaches are like, you can ask or force the users to rate a set of items. You can ask or force the users to rate a set of items. So I don't know whether you have faced it ever, but when I was trying to register for the Netflix, it was forcing me to rate at least 10 movies. Okay, so at the time of registration itself, it is forcing, the system forces you to rate some items. That way, the profile will not be empty, and using that information that is taken at the time of the registration, it can make recommendations to you. This is one approach. You can use another method in the initial phase which doesn't suffer from the cold start problem. Like for example, content based, it will not suffer from the cold start problem, right? Because the recommendation is based on similarities, right? So it will not suffer from the cold start problem. So you can use any method that doesn't suffer from the cold start problem at the initial phase, and once you get the sufficient number of ratings, then you can go for the collaborative filtering approach. Or you can use default voting, like you can assign some default values to the items that that only one of the two users to be compared has rated. Like you can initially you can use, like for example, I'm a lecturer. There may be some lecturers in the system, right? You can use their rating initially to make the recommendation. You can use some default voting, a default rating initially. Some alternative or better algorithms are like, you can assume the transitivity of the neighbors. Like for example, let's say that this this rating also not known to me, and this is the user who are most similar to me, right? So first I can make the prediction for this rating, and using this rating I can make the prediction for this rating. So you can apply the transitivity of the similarity between the users. So these are the some of the better alternatives. So with this, let's move on to the model-based collaborative filtering. So far, let me conclude whatever that we have discussed so far. We have discussed what is recommender systems and what is the relationship between the recommender systems and IoT systems, and different paradigms of the recommender system, collaborative filtering, content-based, hybrid, knowledge-based and hybrid. Right. After that, we are trying to discuss this collaborative filtering in detail. In that, we have identified two broad categories of the collaborative prediction. One is the neighborhood-based collaborative prediction. The other one is the model-based collaborative prediction. So we have completed the memory-based collaborative prediction in our neighborhood-based collaborative prediction, in which we have seen the user-based nearest neighbor collaborative filtering and the item-based nearest neighbor collaborative filtering. Now we are moving on to the model-based collaborative filtering. Moving on to the model-based collaborative filtering, in which I'm particularly discussing the matrix factorization technique. So if you can see this collaborative filtering problem as a matrix completion problem, right? So I've told you that we have given the user item rating matrix, in which some of the entries are observed, some of the entries are unobserved. So our task is to fill these unobserved entries. It means we have to complete the matrix, right? So this can be seen as a matrix completion problem, right? So wherein we are trying to identify the unobserved entries and fill them, right? So our task is to identify this unobserved entries, predict these unobserved entries. So what the matrix factorization is doing is that it is identifying the two latent factor matrices such that when you multiply them, you get this original matrix back. So given the rating matrix Y, which is of size n by m, where n is the number of users and m is the number of items, you want to find out two matrices U and V such that when you multiply them, you get this matrix back wherever the observed entries are present. So you're comparing wherever the observed entries are present. So in your process, what you are doing, you're also learning this unobserved entries. We'll see how that is happening. So let me take a binary rating matrix in which 1 indicates the user liked it, -1 indicates the user disliked it. And some of the entries are unobserved, which are indicated with a 0 in this matrix. So this is a user item rating matrix with a binary preferences. 1 indicates user liked it, -1 indicates the user have disliked it, and 0 indicates it is unobserved. And the task is to predict unknown entries. So if you look at this, you are learning to latent factors matrices U and V such that when you multiply these matrices, you will get the original rating matrix. So our task is to find out U and V such that when you multiply them, you get the original values back wherever the observed entries are present. Like for example, you see this one is observed entry here. So you're getting a value close to this 0.95, -1 here. You're getting a value close to it, -0.81. Let's take another -1 here. So here also -0.81, right? -1 here, -0.8, right? So similarly, 1 here, 1.16 here. So we want to learn two latent factors such that when you multiply them, you get the matrix, original matrix back wherever the observed entries are present. So in this process, not only that you are getting the original values close to the actual values, observed entries close to the actual values, but also simultaneously you are predicting for the unknown entries. You can see that here it is -0.24. It means you can take it as a -1. It is 0.84. You can take it as a 1, right? So in this process, you're also learning these unknown entries, right? So now coming back to this U and V, the latent factors that we are saying. What are these latent factors, right? So we say that U is the user latent factors and V is the item latent factors. User latent factors and the item latent factors. So let's say that these latent factors are the some features that you are learning to map the preferences of the users and the items, right? So just for the sake of understanding, I have assumed here it as the two features are the drama and the comedy. But in general, we don't know what are these latent features or the latent factors. So let's assume that these two latent factors are the drama and comedy. And this is user preferences. The entries indicates user preferences about these latent factors. Like for example, here minus 0.3 means he is not inclined towards drama related movies. User 1 minus 0.5, it means he's not inclined to the towards the comedy type movies. Similarly, you see this user 4 0.63, it means that he likes drama movies, but he dislikes this comedy type movies, right? So now this is the user preference, and this is the item content, whether this movie has a drama or a comedy, to what degree they have. Like for example, you see this has a drama content, right? 0.5 is the positive number, and this has no comedy content, minus 0.97. Now you consider user 4 and item 4, user 4 and item 4. So if you look at the interactions, user 4 doesn't like comedy movies, and this item 4 doesn't have the comedy content, and user 4 likes drama content, item 4 has drama content, right? So when you multiply them, what would you get? 0.63 times 0.55 plus minus 0.84 times minus 0.97. So their interaction is positive, because whatever the user is liking, that is there in the movie. Whatever the user is not liking, that is not there in the movie. So their interaction should be positive. So that's why you have got this entry as 1.16, which is indicating that user would like it to the higher degree, right? Similarly, if you look at another example, let's say that, so this one, user 1 and item 1, right? So user is not liking the drama, item also not having this drama content, very less drama content is present. And similarly, the user is not liking the comedy, but the item 1 has a comedy content to the larger extent. That is why we got the negative value here, right? So like that, you can identify the latent factors. Latent factors, what are they? We don't know. Whether it is a drama, comedy, what it is, we don't know, right? But this is trying to identify the interaction between the user latent factors and the item latent factors, and it trying to map the users with the items. In the process of mapping this users with the items through these latent factors or all the known entries, it is also simultaneously learning for the unknown entries, right? So is that clear? Are you with me so far?
Yes, sir. Yes, sir. It is clear.
Yeah. So this is what the matrix factorization is doing, right? So there are different types of matrix factorization techniques. It's not possible to discuss all of them based on the kind of objective function that they employ, and based on the regularization technique that they take, and based on the constraint that they impose. We have various kinds of matrix factorization techniques. We'll see some of them. Regularization matrix factorization is one of them, which uses the square laws and the regularization term. So here, if you see that when you multiply a row in the user latent factor and a column in the item latent factor, you will get the corresponding prediction. Like for example, when I multiply this with this, I'm getting a prediction for user 1 and item 1. Similarly, when I multiply this with item 2 latent factors, I get a prediction here, right? So like that, when I multiply ui and v transpose, uik and vkj transpose, I get a one particular entry, right? When I multiply uv transpose, I will get a particular entry, ui times vj transpose. I'll get a particular entry, which is yij. So what is my aim? My aim is to reduce the difference between actual and predicted over all the observed entries, right? So this is a actual rating value, and this is the predicted rating value. I want to minimize the difference between them. That's why I've taken the squared loss here, and this I'm doing it for all the observed entries. Here sigma indicates all the observed entries. Wherever the ratings are present, I'm doing this. I'm trying to minimize the difference between actual and the predicted over all the observed entries. And this is a regularization term I'm adding here to avoid the overfitting problem, right? So this is a regularized matrix factorization, as we have a regularization term here, right? And now the question is, how do you any query? Right. So how do you learn this UNV such that the difference between actual and the estimated is minimized? Is the question now. So if you have idea about the machine learning algorithms, it's very easy. Using the gradient descent algorithm or any of the optimization techniques, you can learn UNV such that this objective is achieved. What is our objective? Our objective is to minimize this loss. What is the loss? Loss is the difference between actual and the predicted. And our objective is to minimize this loss. So I have to update UNV such that this is minimized, right? So here UNV are the parameters that I have to learn. It means initially I am initializing them to some random numbers, and gradually I update them such that the difference is minimized, right? So I'll give you a very simple example to do that. So here we are doing the gradient descent algorithm to update this UNV. I'll give you an example to understand that how the gradient descent algorithm works. So remember, this is a j, which is our objective function that we want to minimize, and u and v are the parameters, right? So let's take my theta equal to u and v. So right, now I have an objective function j, which I want to minimize, and I have a theta, which are the parameters, right? So now my objective function is looking something like this, let's say, right? So this is my objective function that I want to minimize. Sukanta madam, how to get the observed entries? I'll tell you. Non-observed. What is your question? How to get the observed are given to us.
Yes, non-observed and observed, that your U and V, that this profile.
Yeah. No, she's asking about observed entries.
Yes.
Observed entries are given to us, right? Observed entries means what? Wherever the ratings are known to us. So if you see this, these are all the observed entries, right? So we have a user profile. User has rated certain items. Like for example, user 1 has rated item 1, 2, and 4. Is not rated item 3 here. So from the user profile, we get these ratings and we frame them in a user item rating matrix. So we have information like, right, user 1 has rated item 1 with the ratings, what is that? Let's say 2. User 1 has rated item 2 with rating 1. User 1 rated item 4 with a rating 5. Like this, we have the information. So from this information, we get this user item rating matrix. Is that clear? Sukanta madam. Is she there? Yes, thank you. Okay, cool. Now we have this objective that we want to minimize. Now the question is, how do we learn the parameters u and v such that this is minimized? How do we learn two matrices u and v such that this is minimized? It's not that I'll be chanting some mantra, Om Boom Bush, and I'm selecting this u and v, and that will be the optimal u and v. That is minimizing the difference between actual and the predicted. That can never happen, isn't it? When you randomly select u and v, it will be somewhere. It's not necessarily the u and v that is minimizing the difference between actual and predicted, isn't it? So you cannot say the randomly selected u and v is the best u and v. So there should be some process through which you are optimizing this u and v, isn't it? So that process is the gradient descent algorithm. So this is the j, which is my objective function that I want to minimize, and these are the theta, which are the parameters of model that I want to learn such that j is minimized, right? So it means that I want to learn the theta corresponding to this, which is very minimal point. So this is the minimal point. I want to learn theta corresponding to it. Theta can be u and v, theta can be anything, right? Right. So now this is what the theta that I want to minimize, right? Right. So now when I randomly initialize, let's say that my parameter is somewhere here, theta is somewhere here. Okay, so what is the slope of the function here? If I look at the slope of the function is negative here. It is descending, isn't it? The slope is negative here, right? So this is the theta corresponding to this value. So now, do I have to increment theta or decrement theta to reach to the optimal point? Increment or decrement to reach to the optimal point of the theta? I have to increment theta, right, to reach to this optimal point, isn't it? If I am somewhere here, I have to increment theta to reach to the optimal point. Am I right? Yes or no? You can reply in the chat box if you are feeling shy to speak up. Am I right or not? If the slope is, yes, cool, right? If the slope is negative, I have to increment theta to reach to the optimal point. Similarly, let's say that when I randomly initialize, my theta is somewhere here. Means the slope is positive. It means it is in ascending direction. The slope is positive, right? It means my theta is somewhere here corresponding to this, right? So to reach to the optimal point, what do I have to do here? Increment or decrement? I have to decrement, right, to reach to the optimal point. From here to here, if I have to reach, I have to decrement theta to reach to the optimal point, isn't it? So when the slope is positive, I have to decrement theta. When the slope is negative, I have to increment theta to reach to the optimal point. So that's what precisely this gradient descent algorithm does, right? If the slope is positive, it decrements the corresponding parameter, and if the slope is negative, it increments the corresponding parameter. But now the question is, how do we get the slope? How do we get the slope, right? So let me give you a very simple example, which is equation of the line y equal to mx plus c, which is a very simple function, right? So if I take the equation of the line, and this is x, this is y, and this is mx plus c. This is the line equation mx plus c. So how do I get the slope? So what is the slope? As I vary a particular variable, what is the slope of that function, right? Is it in ascent direction, or is it in descent direction, or is it in a neutral direction, right? With respect to some variable, I have to determine. Suppose I want to determine what is the slope of this function mx plus c, slope of this function y, with respect to a variable x. What it is? It is in positive slope, right? With respect to x. How do I get that? If I take the derivative of this y with respect to x, what do we get? I get m, right? And which is the slope of this function? The slope is m, and here is x says how far we are along, y says how far we are up, and c is value of this y when x equivalent to 0, right? So here m is the slope. And how do we get this slope with respect to x? By taking the derivative of this function with respect to x, I get the slope. Similarly, if I want to get slope of a particular function with respect to a particular variable, what do I have to do? I have to take the derivative of that function with respect to that variable. It's as simple as that. And if the slope is negative, I have to increment it. If the slope is positive, I have to decrement it. That's all. So that's what here the gradient descent algorithm is doing. So for each element in u and v, what it is doing, it is trying to find out the slope with respect to that element. So derivative of the j with respect to this element, if this is positive, what are you doing? UIP minus constant times positive, right? So it is some step size, ignore that for now. So this is the positive, overall it is positive. If this is positive, what are you doing? You are decrementing because there is a negative sign here, right? So u equal to u minus derivative of j with respect to u, some element u, don't worry about that, right? So if this is positive, it means what? You are decrementing u. If this is negative, what are you doing? Negative times negative, it is positive. It means what? You are incrementing that. So in that process, you are learning this u and v using the gradient descent algorithm. So this, you are considering each and every element of this u and v matrices as a parameter, and you are learning these parameters through the gradient descent algorithm. Any queries you can ask here? Is that clear? or should I repeat it, or shall I
Yes,
proceed?
sir. You can proceed.
Okay, all right. That's how you can learn this U and V. This is when you take the derivative with respect to U in a vectorized notation, this is what you get. When you take the derivative of J with respect to V in a matrix form, this is what you get. So this is the derivative of J with respect to U, and this is derivative of J with respect to V. So you can solve it and see whether you're getting the same or not. So like I have mentioned now, depending on the constraint that the algorithm imposes, depending on the objective function that they take, and depending on the regularization term they take, we have different matrix factorization techniques. In non-negative matrix factorization, there is a constraint. Constraint is what? U and V must be greater than or equal to 0. So here W and H is equivalent to U and V in our previous notations. So this is the constraint that it is imposing, right? And there are different other algorithms. This is a geometrical interpretation of the matrix factorization. As we don't have much time, I'll quickly go through it. I'll just explain you that what is the interpretation. It assumes that rows of the V are the points in the n-dimensional space, and rows of the U is a separating hyperplane that learns user preferences. Right? If you know the support vector missions, there we are trying to learn a separating hyperplane, right? Which is separating the negative instances from the positive instances. So here the instances are the rows of the V, and separating hyperplane is the columns of the U, rows of the U, right? Right. So here you are just taking the rows of U as a separating hyperplane. So one hyperplane may separate like this, another hyperplane, which means another user may separate like this, another user may separate like this, because individual users' preferences are different. So according to user one, let's say that this is user one hyperplane, this is user two hyperplane, this is user three hyperplane. So according to user one, all these are the negative preferences and all these are the positive preferences. According to user 2, all these are the negative preferences, all these are the positive preferences. According to user 3, all these are the negative preferences, all these are the positive preferences. Like this, you can learn these hyperplanes in terms of U and V such that for all the observed entries, wherever the negative instances are present, the corresponding atom latent factors comes one side, and positive instances corresponding item vectors comes other side of the plane. These are the example. So when I randomly initialize U and V, so this is initially, this is how the hyperplanes are separating them. One user hyperplanes, right? In a rating 1 to 5. So as we proceed to the number of iterations, you can see the hyperplane separation for one user, right? So these are all the items with rating 1, items with rating 2, rating 3, rating 4, rating 5. And these are the separating hyperplanes. So this is the maximum margin matrix factorization. You can type it and see, you will get one paper. If you are interested, you can go through it. I'm skipping this, so it requires more detail. So these are some of the references. Thank you very much. Happy learning. I know that towards the end, geometrical interpretation is not so clear to you all, but we don't have much time. But I hope at least till the matrix factorization, it is very clear. If you have any queries, I can take. We have another 2 minutes, 1 minute. But anyhow, we can take, I think with the permission of the coordinators, we can take 5 minutes if you have any queries.
Yes, if you have any queries, so you can ask to sir.
I just have a query regarding the factorization.
Yes, sir. Tell me, sir, what is your query?
Explain.
Sir, I think your voice is breaking. Are you speaking?
Sir, your voice is not clear.
Oh, my voice is not clear. Oh.
No, your voice is clear, sir.
Okay,
I'm
okay.
talking about
Rajesh.
Yes, sir.
Rajesh, sir.
Like I'm.
You can type if you have problem
Okay,
in
sir.
Yes, sir.
speaking.
You can type it. Type here also.
Any other query? By the time he types his query.
So, any other queries from any participants?
Thank you very much, Abhishek sir and Joyla sir, for the opportunity. Thanks a lot.
Thank you so much, sir. And this is our opportunity that we learned a lot of things from you, sir, and your presentation. And this is wonderful information for us. And thank you for sharing a lot of information about recommendation system. Sir, there is a question, sir. What is result of factorization?
What is the result of the factorization?
Factorization.
See, sir, we are learning the two matrices U and V such that when you multiply them, you get the unknown ratings and the known ratings. Known ratings as close as possible to the actual values. In that process, we are also learning the unknown ratings, isn't it, sir? So, our goal is that, right? Our goal of the collaborative filtering is to learn this unknown ratings. So the result is learning the unknown ratings. So let me go back to that. So if you look at this, so these are all the unknown ratings that you are interested to learn, isn't it? All zeros. This is the binary rating. We can similarly imagine it for the numerical rating also, with a range of 1 to 5 or 1 to 10, whatever it is. Right. So your goal is to predict these unknown ratings, isn't it, sir? So once you get the resultant metrics, so you can convert them to ones and minus one. Anything greater than 0 to 1, anything less than 0 to minus 1. Right. So in that process, what are we doing? We are also learning these unknown ratings, isn't it, sir? So you can see this. You can see this minus 1. This is minus 1. So this is plus 1. This is plus 1. All these are the unknown ratings, isn't it, sir? So we are learning these unknown ratings in this process. So that's what we are aiming at, right? In collaborative filtering, our goal is to learn these unknown ratings. That's what we are achieving. Is that clear, sir? Rajesh, sir?
So Rajesh sir, I think his voice is not clear. Maybe if you have any question, you can drop a mail to sir directly. Any
You
participants.
can ask here also. You can express it whether it is clear or not to you.
Yes.
In the chat box also you can do that. So that if it is not clear, I can explain.
So I think, sir, now he is unavailable.
Okay. All right.
Okay, sir. So once again, thank you so much, sir, for your